Hey class, this is Professor Rourke. I wanted to make a video about the 7.2 homework on Webassign. 7.2 is all about trigonometric integrals. So integrals that already have typically sine, cosine, some tangents and secants, and some cotangents and cosecants, possibly, all sort of jumbled in there together, often raised to a certain power. And then we are supposed to use our knowledge of Pythagorean identities and a combination of u-sub. Every now and then they bust out integration by parts, right? All of these things kind of mixed in together to evaluate some of these integrals. And I know this section can be challenging because we just were sort of expected to master u-sub, and then we were expected to master integration by parts, and now the hits just keep coming, right? So I know this is a chapter in general that can sort of feel like, oh my goodness, lose sight of what's going on and why we're doing this. So I just want to make a video to hopefully make you feel a bit better. Some of these problems do take some time, but they shouldn't hopefully cause you too much where you are spending more than like an hour trying to figure out even like what's happening, right? So if you find that the case, let me know. It probably might just need a little bit of information or some insight on this. So for instance, number 12 on this particular homework is a definite integral. So it's like, okay, I know I'm going to have to end this with evaluating some trig of the unit circle and such, but that's all right. I'll deal with that later. And then it's cotangent to the fifth of, and then they use the lovely Greek letter phi just to really, make it look lovely, times cosecant to the third of phi, all in like d phi, all respect to phi. So first of all, I'm going to use x's for this problem. I have enough issues trying to write on the computer, let alone trying to use a uncomfortable to my hand Greek letter. So we're going to switch over to x's and call it a day. So one thing that could be causing you some concern when you first look at this is like, hold on a second. Like we have done some combination of sine squared and cosine squared. We've done tan squared and secant squared. I know those are related, but we haven't really seen the third stepchild here much involving cotangent and cosecant. So the first thing is this is essentially going to follow the same patterns we've done before. It just might not often feel like it's definitely the one that's like mostly left to the side because like we feel fairly confident, hopefully, with sine squared plus cosine squared equals 1. Hopefully that's okay. And if we had to, we could derive in terms of tangent, right? We could divide everything by cosine squared and get that tangent squared plus 1 equals secant squared. Okay, fine. However, there's technically the third option where if we take sine squared plus cosine squared equals 1 and divide everything by sine squared, we would get 1 plus cotangent squared equals cosecant squared. Okay. The other part of this that I like to always just sort of have like a brain dump when I first start my assignment or even mid assignment, if I'm like, ooh, I kind of forgot about this. The derivative of cotangent, we do want to feel comfortable with being able to do this because the whole name of the game for this section is to sort of set aside something from my original expression so that it's like a du is set off, hanging out, waiting to be used. Okay. And so the whole, if we're going to set aside something that's du, we need to know like what is du, like what are the derivatives of these trig equations, right? These trig expressions. So for instance, the derivative of cotangent is going to be essential, and also the derivative of cosecant. So this is also part of why this problem's like the third one that everyone often forgets about, is because, yeah, fine, we can define the derivatives of sine, cosine, tangent, and secant mostly. But cotangent and cosecant are like the least frequent, I'd say, but they follow the same pattern, right? So if you know that tangent, the derivative of tangent is secant squared, cotangent's really quite similar. The derivative of cotangent would be cosecant squared, and it's just happens to be negative. Okay, so it does follow again the same pattern. If you can get tangent and secant, you can get cotangent and cosecant. And then the derivative of cosecant, same vibes. The derivative of secant is secant x tangent x. Derivative of cosecant is just cosecant cotangent, right? Kind of makes sense. And it also is negative. Okay, because any derivative of a trig function that starts with a C often has a negative in front of it, which we learned from one of our classmates last year, which I think was very helpful. Okay. So all of that's there. Okay, brain dump time. Now let's go back to the original problem and see what's going on. So we have cotangent to the fifth again, and we have cosecant to the third. So this is when we start thinking like, okay, what would be like a good possible du that I could pull off to the side? I know in theory on the textbook that I had you guys write down for the notes on, it like breaks down like if secant is even, if tangent is odd, all those things, right? But it is helpful to sort of know like why those are. That's because we're trying to figure out what's a good du. All right, it's all about rewriting this so that the du is multiplied off to the side, and we can then use a trig identity to make it easier so that everything can be turned to a u nice and easily, and then we have the du like ready to go. Okay, so like for instance, you might start thinking like, okay, let me see. I see a cosecant to the third. I know the derivative of cotangent is cosecant squared, negative cosecant squared, but the negative is something we can handle pretty easy using u-sub. But then let's say let's pretend in our brains that we maybe rewrote this with the cosecant squared towards the end. So instead we had cotangent to the fifth times cosecant times cotangent to cosecant. I don't really see how that would help us, right? Like if we had u equal cotangent, then we would have like u to the fifth, and then we have this like random cosecant, and then we have like a du, but then what about the other cosecant, right? Like that, we wouldn't really get very far. And sometimes that can be frustrating here because you might try that route, and then you're like, oh, I have some regrets. So we have to try to think these things through, like sort of like walk through them a little bit beyond to see what we could possibly have. Like for instance, okay, whether or not you sort of followed my train of thought, the cotangent, if we've got everything in terms of cotangent, it doesn't really work out really well because like cosecant squared, we have another cosecant. So let's then instead maybe think about if I rewrote it with the other option here, with I had like cosecant cotangent off to the side. Okay, so if I have a cosecant and a cotangent written off to the side to be my lovely du, I would then be left with like a cotangent to the fourth and a cosecant squared, which then we might be cooking with gas because then I have cotangent to the fourth. That's even. I could bust out one of the trig identities. Cosecant squared, I have the option of a trig identity there, right? So I think that might be the better direction to go at this point. Okay, so that just sort of explained like my train of thought. I know sometimes these again are very overwhelming. We're throwing a lot of information at you in a quick amount of time, but typically if you have some combination of either sine and cosine or tan and secant or cotangent and cosecant even raised to certain powers, we want to try to rewrite them so that we have a nice du off to the side, and yeah, just kind of go from there. Okay. All right, so I'm going to go ahead and rewrite this problem. I'm just going to forget phi. I'm over that. That's enough. That's just enough. I'm going to go back to x, okay? So we have the integral from pi over 4 to pi over 2 of cotangent to the fourth times cosecant squared x dx. Okay, and then, well, actually, you know what? I lied. Let me go ahead and fit in here before I write dx, just to keep it hopefully as easy as possible. I'm going to write cotangent x cosecant x dx. Okay, so I haven't changed anything at all about my original problem. All I did is instead of writing cotangent to the fifth, I rewrote cotangent to the fourth, and then I just put the other factor of cotangent on the right hand side, and then same thing with cosecant. Instead of writing cosecant to the third, I just rewrote this as cosecant squared, and I put the cosecant to the right. Okay, so hopefully if you take a look at that, like, yeah, it can make sense, right? And this is again the main idea of what we're going to do, because if we have du cotangent cosecant or cosecant cotangent, however you want to say it, that is the derivative of cosecant, right? So if I can get everything here in terms of cosecant, then I can make a u equal cosecant, and I already have my du like ready to go. This essential part over here, this d cotangent cosecant, that's what I want to be my du. Okay, so let's try that out. I'm gonna go back to my trig identities. This is the third one that we often don't really use as much, but is still there. Okay, it's still like you. 1 plus cotangent squared equals cosecant squared. So in other words, cotangent squared is equal to cosecant squared minus 1. Okay, and then hopefully it also makes sense. Like if I need cotangent to the fourth, that would mean I just need to square my expression. So instead of just having cosecant squared x minus 1, I would have the quantity cosecant squared x minus 1 squared. Okay, so I'm going to go ahead and sub that in for my cotangent, and then I have everything in terms of cosecant, and it might get bumpy along the way, but then that's mostly the trig part that we need to know. That's the trig knowledge that we need. The rest of it from there is like algebra, painful algebra often, but that's okay. Okay, so I'm going to go ahead and rewrite this as cosecant squared minus 1 squared times cosecant squared x, and then here's my cotangent x cosecant x dx. Okay, so let me pause real quick. One question that I often have here is u. So I see a lot of cosecant squared, so that should be my u, right? Like u is cosecant squared. No, sorry, that's not what you want to do. You just want to make u just cosecant, not cosecant squared, because the whole reason we did all of this was so that we would have a nice and easy du, which is cotangent cosecant. If I have cosecant squared, that's not really my derivative anymore. That wouldn't be du, right? I would have to bust out a little bit of a chain rule, which wouldn't be the end of the world. It'd be fine, but that's not what I set out to do. I just set out to have du as cosecant cotangent. I'm not trying to change that right now. Okay, you could possibly, if this doesn't work, but I don't really want to do that. Okay, so u is cosecant x. Okay, and then we're like, what's du? Like, I know, I just talked about this. This is going to be negative cosecant x cotangent x. Every now and then this pen gets me. Okay, negative cosecant x cotangent x dx. Okay, now we don't have negative cosecant cotangent x dx, we have positive. So when I make my u sub, I'm going to go ahead and sub in negative du, okay, instead of positive du. Okay, what else do I need to do here? Unfortunately, this is a definite integral, so there's bounds, but which is, I know, it's just like sometimes it's a bridge too far. It's like, come on, really? But that's okay. What we're going to do now is we're going to turn over our bounds from pi over 4 to pi over 2 into u, okay? And that way we don't have to look back at cosecant. We'll be done, okay? So this will help us. It might not feel like it right now, okay? So let's start. I usually start with the lower one, but it's up to you. So x equals pi over 4. If x equals pi over 4, what does u equal? Well, that would be like cosecant of pi over 4. Which I'm sure you're like, oh, come on. But that's square root of 2. Okay. I know the unit circle is just sometimes just not kind to us, but hopefully you'll be like, okay, all right, that's fine. And then I have to do cosecant of pi over 2, which is just 1. Okay, so now we're going to switch on over to u. So since I'm switching over to u, I'm also taking into mind, like, if I have to like compensate for anything with du. So I'm going to go ahead and pull out a negative at this point in time, because when I make my swap for du, my negative du is actually equal to cosecant x cotangent x, which is what I have. Okay, for my bounds, I don't have to do pi over 4 to pi over 2 anymore. I don't know if it's much better, but I'm just going to go from square root of 2 to 1, and then we like are saying goodbye to cosecant for now. Okay, we're not going to have to ever put cosecant back in. And again, it's just because there's bounds. If there wasn't bounds, the cosecant would be back. But there are bounds, so we're done for now. We turned it over to u. Okay, so this is lovely. I have the integral of square root of 2 to 1, and then of u squared minus 1, the quantity squared, times u squared du. Okay, so now we're moving into algebra territory, okay, which can get bumpy, I know. If we were to square u squared minus 1, it's actually u to the 4th minus 2u squared plus 1. I know. And then I also still have a u squared hanging out there that needs to be expanded. So just be careful with these algebra steps. Take your time. Try not to rush through them. I know it can be a bit painful, but I have faith that we're going to make it through. Okay, so if I expanded it correctly and then distributed in the u squared, I'd have u to the 6th minus 2u to the 4th plus u squared du. Okie dokie. I think I'm now ready to take the antiderivative, right? Like, I can do this. I can take the antiderivative of u to the 6th. I can take the antiderivative of 2u to the 4th, and I can take the antiderivative of u squared. I got it where I want it, even if it's not great. I can do this. So what I'm going to go ahead and do, I typically use brackets when I'm actually finding the antiderivative. That's also sometimes a question is like, where does the du go? Or when do I drop the du? Things like that, right? This is it. When you take the antiderivative, this is where you drop the integral, right? And also drop du. Now, if this was an indefinite integral, right, without any numbers for my bounds, I would have to add in the plus c at the end. But we're going to have to evaluate this after we find the antiderivative. Sometimes I'll say like f of b minus f of a, like with a capital F. So if the function is usually used with like a lowercase f, the antiderivative is also often used as like a capital F to say like, oh, I took the antiderivative and now I'm going to like evaluate it at its bounds. So sometimes if you hear me say f of b minus f of a, that's what I'm talking about, is like, okay, I'm finding the antiderivative and then I'm evaluating it at its bounds. Okay. So I'm going to go take the antiderivative now. The antiderivative of u to the 6th would be 1/7, u to the 7th. The antiderivative of 2u to the 4th, I'm going to say minus, I become a 5th, 2/5, u to the 5th. And then lastly, the antiderivative of u squared would be 1/3 u to the 3rd. It's not the most kind with fractions, but you know, I think we'll make it. We'll be all right. One option here as well, you don't have to do this. You might see a lot of different ways of sort of like going from here. I don't really love that negative hanging out front. So what I could do is I could rearrange my bounds, because if you remember some of those integral rules, that's a 7, by the way. 1/7 u to the 7th minus 2/5 u to the 5th plus 1/3 u to the 3rd. I could just switch these and then it would take care of the negative. Okay, because if you remember, integrals are, if you switch the bounds, are equal to the opposite sign of the original integral. So if I just flippy-flop the square root of 2 and 1, I can drop the negative. So if you see that, you don't have to do that. You could just keep the negative there and have kept it as like f of 1 minus f of the square root of 2. But why not? You know, it's okay. We could do this. Okay, so now I'm gonna go ahead and evaluate this with the square root of 2 first. Like, whew, that's gonna smart a bit. So let's think about this. We have 1/7. I have the square root of 2 to the 7th, which is pretty gross. But let's think. I'm gonna have a square root of 2 left over. That's for certain. But the square root of 2 to the 6th would be like the square root of 2 times the square root of 2, right? Which is 2. 3 times. Does that make sense? Like, because it's like the square root of 2 to the 6th would be like the same thing as 2 to the 3rd. That sort of kind of makes sense. So whether you can use your calculator as well, but the square root of 2 to the 6th is 8, and then I have the square root of 2 left over. Okay, and then I'm going to keep going. Minus 2/5, and I'm going to try the same little thing I did there. So the square root of 2 to the 5th is the same thing as like, I'm going to have one of the square root of 2's left over because it's odd. So it's just going to be there. But square root of 2 to the 4th would be like the square root of 2 times the square root of 2 times the square root of 2 times the square root of 2, which would just be like 2 times 2, which is 4. I know I've got some odd choices for my writing right now, but that's okay. And then last but not least, I have 1/3 square root of 2 to the 3rd. Like, why couldn't we have this like one even exponent to make this nicer? But that's all right. So this is going to come down to like the square root of 2 squared is just 2, and I have another square root of 2 left over. Like, come on, man, just couldn't have made it like one of the square root of 2's go away, but that's okay. All right, and then I'm gonna say minus, this is all gonna be when I plug in 1. So we'll just have like 1/7 minus 2/5 plus 1/3. Whew. Now remember, for tests and things like that, you're always gonna have your graphing calculator. So you're more than welcome to put like this fraction part in here and the end in your graphing calculator, and then just do the math fraction button. It could really save some time. And the same thing applies for what, even if we do have a radical, we can still use the calculator to our advantage for the parts that don't have the radical, right? So the kind of good thing, well, I guess it kind of works out. All of these have a square root of 2, right? So I could think about it as like taking the square root of 2 out. And then I would just be left with essentially like 8/7 minus 8/5 plus 2/3, right? And do a little math fraction in the calculator to get a common denominator. Could possibly be helpful to me at this point in time. Like, so for instance, if I use my calculator now to do 1/7 minus 2/5 plus 1/3 1/3, and then I do math fraction, it tells me 8 over 105. Right? Now, I could have figured that out, right, the long way, but also, it probably would have hurt a little bit somewhere in there. Just like, we've done enough. We have. So, if we do that on the left-hand side, I would get 8 over 7 minus 8 over 5 plus 2 over 3 is 22 over 105. So I'm just going to write that as 22 times the square root of 2 over 105 minus 8 over 105. So if you really wanted to, you could also put this under one denominator, but it's up to you. It's however you want to do this. Okay, so I know that's a lovely number. And whatever's easiest for you, you can type that in. So hopefully this kind of makes sense, the general idea of where we started. I know getting stuck down at the end with the different bounds can be a bit painful, but in the beginning, the whole idea is that we look for the trig identity that works for our problem, possibly, right? And then the key is to know what the derivatives of those trig functions are, because that is going to be what we need to set aside as du. Once we do that, it can be painful, as we saw, with some pies and some square roots and things like that, and fractions, all of those things combined together. But overall, that's just going to be like the key is the first part, understanding the trig identities, understanding what we can pull out as du, and then going over to u-substitution. Okay, I know it can get a little rough in between, but hopefully that was helpful. Again, that was number 12 from the trig integrals Webassign assignment. I'm going to make a different video talking a little bit about what you want to look for in 13 and 14. I'm not going to work them completely through, but just sort of like an overall idea that if you're not really sure which direction to go, to kind of get you started. So please keep me posted. I can always make videos and send them out if it's helpful. Don't forget my office hour times and also the options that you have for all of the tutoring helps that the college has for you. They pay those wages are paid from your tuition costs, so you might as well use them, right? In addition to my office hours. So please let me know how I can help, and I will talk to you soon. Thanks.